Good morning, ladies and gentlemen. In my report, I would like to talk about thermal analysis. I think that the audience is well prepared and everybody knows why it is necessary to perform thermal analysis of the ground. I will briefly talk about it. In the construction of buildings on permafrost, there is a risk of ground melting under the thermal influence of buildings, foundations, pipelines, and any other facility that is located on the frozen ground. As a result of ground melting, the disasters as shown in the pictures may occur, i.e. damaged pipelines, buildings, etc. Knowing the temperature distribution in the ground, we can predict the ground subsidence, frost heave, bearing capacity of structures, etc. Which solutions does our company offer in this area? We have developed the Frost 3D software for thermal analysis of the ground. The software is required during the design of such facilities as pipelines, railways, foundations on permafrost, as well as when using artificial ground freezing technology in construction engineering. This technology is in high demand for the construction of tunnels, dams, and embankments. The software is certified in Russia. I will not go into details because we have a video explaining how to use the software on our website. Today we'll also have meetings with companies and workshops demonstrating the functionality of the software. I will first demonstrate the Frost 3D workflow, which involves 3 simple steps. The first one is the 2D model creation. Design engineers may upload background images or topographical plans, for example, to reconstruct the surface of a modeling site, or upload the plan of cooling device installations. In this particular example, we can see a system of passive thermosiphons. All this is created intuitively and delineated by special tools. The altitudes are set, and the ground levels that are located in the section for boreholes are set. This process is drawn very quickly in 2D, and there is no need to create complex 3D models. Frost 3D then automatically reconstructs the 2D drawing in 3D. The user can check the reconstruction for errors and check the precision of created objects in vertical and inclined cooling devices. If something is not right, the user can go back a step and address the problem. The next step is meshing the computational domain. Here we've zoomed into a very small area to demonstrate the level of detail of the mesh, because our software supports very large meshes. Each model consists of millions of cells, and almost all our calculations are in the order of millions, 2, 5, 10 million cells. At this stage, we also set up the thermophysical parameters of ground layers and all the materials used in the model. We define boundary conditions, initial conditions, and run the computation. It is possible to perform computations for 2, 10, 50 years, etc. If you use known commercial software, it would normally take a very long time to compute such large models, but we have managed to obtain extraordinary computational speeds thanks to NVIDIA technology and the Frost 3D mathematical solver. The last step is post-processing work, where we can analyze the results of thermal distribution in grounds. You can see here how effectively the cooling devices work. The resultant map can be viewed through any section, at any angle, from any perspective, with corresponding values. We can select any point and obtain graphical or tabular dependencies. For design engineers, the most important thing is to see what is happening in a specific section and to be able to perform analysis on Isolines. Here, the animation is presented. There is a special tool in the software which allows you to move the mouse to any position and the isoline is built dynamically at that point. As a result, it is easy to determine the position of the freezing front, amongst other things. One can see where freezing occurs and make project decisions accordingly. I would like to show you some real examples of projects where Frost 3D software has been utilized. Here's the section of the ESP01 Pipeline, Eastern Siberia Pacific Ocean, which is located on permafrost with underground ice deposits. It was necessary to estimate whether the ground melting bulb formations would reach the ice wedges or not, i.e., whether they would thaw or not, and how effective measures such as pipeline trenching and using heat insulation above and below the pipe would be. We have simulated an area of 25 by 25 by 15 meters, and the model consists of 3 million nodes. After 1 year, we can see the temperature distribution in longitudinal and lateral cross-sections. Here is the ground melt bulb formation. In the red area, the ice will melt completely within 1 year. Here is the result after 10 years. If we visually compare the ground melt bulb formation after 1 year and after 10 years, we immediately notice that it is expanded after 10 years. These results enable us to foresee what will happen in 10, 20, or 50 years. It is possible to predict major destructive events decades ahead. The significant feature of the software is that the problem is solved in 3D. There is software on the market that simulates in 2D, but these cannot account for complex ground structures and hence introduce significant computational errors from the outset. In our software, the user can reconstruct any complex ground structures they wish or require. Here is another model. It is a hot oil tank with a flat loop thermosiphon foundation system of one of our clients, Fundamentstrojarkos, located under the tank. The simulation area is larger than in the previous example, with an area covering 90 meters. A very thin heat insulator is located on the site, and this feature essentially affects numerical computations. If you know mathematical and physical aspects of such computations, you will understand that if there are very small elements having dramatically different thermophysical properties, it will significantly complicate the calculation. All known commercial software on the market will have serious problems concerning computational speed in this case. Here are modeling results. We can analyze the effectiveness of cooling devices, make any section, and decide whether it is necessary to increase freezing capacity or not. Here is an interesting example not involving thermal stabilization as in the previous example. It is the application of artificial ground freezing technology. This tunnel in Germany was built in complex hydrological conditions with huge filtration flows, more than 1 meter per day. In order to build this tunnel, it was decided to use artificial ground freezing technology. There was also a need to save very important historical buildings located above the planned tunnel, and ground subsidence was unacceptable there. 23 cooling pipes were installed along the total length of the tunnel, and it was necessary to create a reliable model and calculate the total time of ground freezing before underground tunneling work could begin. It can be seen from this section how groundwater flowed in this direction. Tunnel number 1 became frozen, and so too did the second one, 1 month later. So, on the basis of computer modeling, construction engineers knew that they could start drilling the first tunnel after 2 months of freezing, and the second tunnel would be ready for drilling by the time the first was completed. Our colleague from NVIDIA mentioned this computation. It is extremely interesting. Everyone knows about the disaster which occurred at the Fukushima nuclear power plant, involving lethal concentrations of radiation seepage into the ocean via groundwater. A disastrous event, especially considering how important the environment is to the Japanese. In order to stop radiation seepage, the following solution has been introduced: to freeze the wall around the reactors and create an ice wall to restrict the outflow of groundwater from the radioactive zone. The computation is demonstrative. Here we can see the large size of the site of 0.5 by 0.5 kilometer. Such sites have never been modeled before, because there is no appropriate software on the market. We used this model to test the latest NVIDIA video cards. This model consists of 17 million cells, and the NVIDIA video cards allowed us to perform the computations for such models on a common PC. The computational time for a 2-year simulation period was completed in 6 minutes. In just 6 minutes, we computed the freezing of Fukushima over 2 whole years, demonstrating that we have the capacity to simulate large complexes with our software and the latest NVIDIA video accelerators. We have zoomed into this fragment so you can see the degree of discretization for this site. The size of freezing pipes is measured in centimeters. The size of the site is half a kilometer, so the discretization should be tens of millions of nodes. We also tested even larger models. We computed models with more than 100 million cells on special testing models. Here are the simulation results of the ice wall around the Fukushima nuclear power plant. In the picture below, we can see the freezing front. In the picture above, one may analyze the thermal distribution. In our software, every part of the model can be scaled, and one can make a selection anywhere to observe what is happening there. Without this state-of-the-art GPU technology, Such large models could only be simulated on supercomputers with the help of special platform software tools made for these supercomputers. Moreover, 3D thermal analysis of ground freezing and melting on such large sites would still not be possible to this day. And now, several words about our technology. I will begin by reiterating some information from last year's conference. We are not talking about mathematics and physics today, because we have many conference videos concerning these topics on our YouTube channel. Last year, we announced these results for the first time at this conference and compared our results with such vendors as COMSOL and ANSYS. ANSYS is the worldwide leader in CAE software. Why are we making comparisons with these software packages? To show our advantage. Last year, we announced that we computed the heat transfer problem with phase transition, so-called Stefan problem, several times faster than these vendors. We performed a test computation because you cannot simulate large sites with these software packages. Those were the results of our numerical simulation technology last year, which hadn't yet been parallelized and was written only for a single-core CPU. The results of our technology were 10 times faster than our international competitors. We entered into partnership with NVIDIA, and we have parallelized the algorithms of our mathematical solvers. When we were developing the single-core solvers, we knew about GPGPU technology and factored this technology in. That is why we have obtained such extraordinary parallelization speeds. When we created our mathematical algorithms taking into account their future parallelization, we integrated effective parallelization regimes. Here are the results in comparison with the single-core version. For example, we have parallelized for a quad-core Intel processor and obtained almost four-fold acceleration. In fact, acceleration is not actually linear, i.e. if it takes 1,000 cores, it doesn't mean that there will be a speed increase in the order of 1,000. For example, ANSYS, having transferred its solvers from CPU to GPU, only managed a triple acceleration. This is generally the acceleration ceiling when using graphics adapters. Abacus has also increased its speed by 2 to 3 times. We have sped up our computations by 46 times, and that is why only Simmakers can compute a site consisting of 17 million cells in 6 minutes. We performed computations on the latest NVIDIA video cards. Here the max DOF model gives the number of the degrees of freedom that can be used in various versions of our software. In other words, it is the number of cells that can be theoretically used in models. We haven't computed such huge models with billions of cells, but we are not far away from achieving this. We are already up to resolve models containing 50 million cells with GPU technology. In conclusion, I would like to say that the use of our Frost 3D software is very efficient in performing thermal analysis of constructions located on permafrost. Using our software, you will be able to make the right managerial and technical decisions. Also, right now, there are no analogous software solutions on the market. We will be glad to communicate with you today and show everyone our software in order to let you know more about it. The simulation will be run on a common laptop without using supercomputers. That is all. Thank you for your attention. My question is about the physical model put in your computations. Do you consider any changes of ground properties in the process? Changes in thermal properties of the ground, its heat capacity, a jump during the phase transition are taken into account. In this presentation, we don't have the slide that was shown last year. An abrupt change of thermophysical properties is the biggest problem of all. That's why a lot of software crashes. They don't have convergence, and it becomes impossible to perform computations. We have been working on this problem for many years, and such problems do not exist in our software. Have you compared your results with the experimental data? Of course, we have. It's an issue of verification. Firstly, we perform verifications with analytical solutions. There is no analytical data available for 3D and 2D models. It only exists for single-dimensional problem statements. Last year, we showed a slide with analytical comparisons, and our software had the closest coincidence with the analytical solution in comparison with all the software that we analyzed. We analyzed with ANSYS, COMSOL, and Abacus, and compared them with analytical data too. We also compared some models that could be simulated by these vendors. There is no doubt that they have correct and precise mathematical solvers. The coincidence with the results of the international vendors is very good. Also, comparison with experimental data is a big issue. We began working on this software when we collaborated with Fundamentstrojarkos. This company is a world leader in passive ground freezing equipment production. They have their own sites where they conduct experiments. They shared experimental data with us, and we compared everything. Now they base their thermal analysis work for their customers on our developed mathematical solvers, and all indications are that they are very satisfied. Everyone has questions, and we are always ready to answer them. The point is, it would be more likely for the user to introduce errors rather than the computational algorithms. Indeed, user error, this is the most significant problem for any similar software. We had a situation where a user claimed, "Your software doesn't work. It performs incorrect calculations. What's going on?" We began to analyze his project. For thermal insulation, he had set up the properties of a superconductor. And there are so many errors similar to these, like not writing the proper amount of nulls for a parameter, and in the end, the software produced errors. That is why the user should also be very qualified. All CAE software requires highly qualified engineers to use them properly. Of course, it is possible to teach any person how to work with the software. The main thing is that a person should understand what is happening on a physical level, what he is doing when setting the parameters, what kind of boundary conditions are required, whether it is the first, the second, or the third type. Have you gathered experimental data about the ESP01? You said that you had modeled ESP01. Later we will discuss your computation. The pipe is operating, permafrost is being melted, and there is ground subsidence. An altimeter has been installed, and everything is being monitored. Have you compared the values that you obtained in the software with experimental data? The pipe was buried 2 years ago. We have compared the computation results with 2 years of experimental data and achieved coincidence. The ESP01 wasn't buried 2 years ago. We were given data from 2011 to 2013. We simulated what happened to the pipe during these 2 years according to their data. Another point is that the main problem in Russia is geological examinations. Companies are too lazy to do them, they do examinations incorrectly, send wrong data. I can't say the exact figures. For example, it is necessary to take ground samples every 100 meters, and instead of this, they took samples every kilometer. Human factor is the main problem. We have no doubt about the precision of our software. Another thing is, if at any stage of the initial data input, the user makes big errors or sets incorrect input data, then how can we blame the software? Okay, the question about optimization. Assuming I'm not an expert level user and I place 100 thermal probes and the software shows a positive effect, how can I optimize the number of cooling devices? Does the software allow us to do this? I mean, I need 97 thermal probes instead of 100 and the positive effect will remain. If you mean inverse problem, I can say that we don't solve it. You probably know that this type of problem is complicated enough. In any case, you can see if you have installed 100 thermal probes, and everything became frozen 10 times more than necessary. So we have to determine the number of cooling devices using only enumerative techniques? It means that you will need to recalculate every time? Yes, you are right, but you don't need to recreate the model again and again. You just turn off at the checkbox unnecessary cooling devices and it won't work. Then run the computation, and you don't even need to recreate the mesh in our latest version of the software. You say, enumerative technique, yes, but the run of a new computation will take several minutes. Doesn't the system itself show automatically that these thermal probes are unnecessary? Maybe I've installed too many of them. You told us that it is possible to take them out of the computation if they are not crucial and effective. Software doesn't inform the user where to install thermal probes. There are specialists who are responsible for this, because if we also took responsibility for the installation plan of thermal probes, we would be responsible for the whole engineering process. We are CAE developers. We can simulate. You tell us exactly which problem you want to solve, and we will compute it. You are always saying that you can compute, but maybe it would be better to give them opportunity to compute. You will sell the software, and they will calculate and decide how many thermal probes to install. I don't deny that. I meant we could perform high-quality computations, and if someone comes to us wanting computations, surely we can do it with the highest quality. We can lend our expertise to the project as well. If someone isn't satisfied with the results, we can lend our knowledge to help them. Good afternoon, Dmitry. I'm Nikolai Pavolkovich, Tomsk-Nipineft. I have 4 questions. The first one, you told us several times about the certificate, but I didn't see them on the screen, scan, whatever. We do have it. I will show you. You have compared your software with the foreign ones. Have you made a comparison with the local Russian software? If you tell us which local software exists, we will definitely compare with them. Thermostab, for example. Thermostab software doesn't perform analysis properly. I think you know what this software is. Why doesn't it work? I can explain it later. I don't want to denigrate the company. Okay, right. MSU, Moscow State University, has some developments. We have communicated with the MSU faculty of Permafrost Studies, and I have to say that all these developments are of a scholastic level. Okay, another question. You told us about the custom engineering. Are the results, exclusive rights, and source code given to the customer or not? What do you mean? Do you mean computations? I mean custom software development. It's an issue for discussion. We have to specify what exactly we intend to develop, whether it is based on our framework or a completely new development. It makes a big difference. And the last question, is the software commercial? Do you sell it? Yes.